Dr. Matt again. Oh yeah, as a bonus, as promised, we're gonna get the chance to derive the famous equation E equals mc squared, just based on special relativity rules. Okay, first we need to remember, how things were measured before special relativity. You were separating space and time. For instance, you would give the location of a point in space, using a 3D frame of reference here, 3D, the width, the depth, and the height. And you would say, well, this point here is equal to, 3 units to the right, 2 to the front, and 5 to the ceiling over there, And another way to do that would be to use a vector, something like this, and you would say, well, this vector is equal to 3, 2, 5, the vector OP here. And what's interesting is that when you want to measure the distance between O and P here, you would use what we call a Euclidean distance, which has been defined as the Euclidean norm of this vector. And that is equal to the square root of the sum of the squares of the coordinates. In other words, 9 plus 4 plus 25, and then you take the square root and you get the length here. And what's interesting is that this length, or this vector length of this distance here, will always be the same, even if you change your frame of reference here. And that's what's key with the Euclidean distance here. Now, let's see what happened with special relativity. So to summarize, in the Euclidean world, before the special relativity, the distance is defined as this, and it's invariant from one Galilean frame of reference to another. Now, let's look at the example of a light ray, moving in any type of direction. And the distance that will be traveled by the light ray would be equal to this, by the definition of the Euclidean distance. And therefore, it will be equal to c times t, c being the speed of light and t the time. Therefore, if you raise this to the square, you get, d squared is equal to c squared t squared, or this, which is pretty obvious. But what's interesting is that means this value is constant even if you change the frame of reference, because, the speed of light is the same everywhere. Therefore, this will be always true. So there's this crazy guy, yet another crazy physicist, actually was more like a mathematician, but he said, well, there's this other crazy guy called, Albert Einstein. He says, time and space is related. And therefore, instead of using 3 coordinates, maybe we should use 4, and call them space events. And therefore, it will look like this, x, y, z, and t. And that would be the space-time even definition. But then if we do that, and if we look at the, the norm of the vector here, we could get something like that. And if we assume that x4 is equal to ICT, which means x4 to the square is equal to minus c squared t squared, then you can write that this distance would be equal to that, which is really close to what we get, in the 3D world. So you see, that would be pretty interesting. So let's keep that as, in our memory, because that means that's how we can define a distance for space-time events, with special relativity. What you do is you take, the spatial distance here, and then you do minus c squared and the time coordinates, of the vector to the square, of course. Okay, so let's remember that. And based on that, then what we can do is calculate what we call the relativistic velocity. The velocity is basically the rate at which things change during time, So in our space-time event example, it would be, the derivative of x relative to tau being, it's a Greek letter. It will be, according to Einstein, you would call that the proper time, which means the time relative to the frame of reference, where the particle or the object would be, at rest. And then he said, okay, well, then the velocity would be derivative of x over tau I mean d tau, and then derivative of y relative to tau, and z relative to tau, and of course of time the generic time relative to tau, the proper time. Now, if we assume that we have a frame of reference, f prime moving from the frame of reference f, then we would have, according to special relativity rules, we have the Lorentz factor here, and from that also we can see that the difference in time in the new frame of reference is equal to gamma times the difference in time in the initial frame of reference. You remember? That was something we derived in the previous video. Therefore, we can say that gamma is equal to dt over d tau. Okay? Yeah, okay. Then, from that, now, if we look at, for instance, dx over d tau here, it's equal to dx over dt times dt over d tau, right? And dt over d tau is gamma. Therefore, dx over d tau is equal to gamma times dx over dt. Okay, and same thing, of course, for y and z. And then t, is just equal to gamma here, the time coordinate. Therefore, we can also write it that way, because this is equal to gamma times the velocity in the 3D space world, which we call v here. Okay, and then the final time coordinate here is gamma. And as we've seen just the previous slide, the distance defined by Minkowski says, well, in order to get the square root of the norm here, you get the distance for the spatial coordinates here, so that would be gamma square v square, of course, and then we add minus c square times the time coordinate to square, so that's c square gamma square, okay, and then you factorize gamma square and you get minus c square, okay, so don't worry, this is square and this is a negative number, but we're using complex numbers here, but let's not confuse ourselves with this anymore. And then there is a first intuition here by Einstein. He says, well, let's see, if we multiply everything by m, this is what we get. We get the m here, and the m here, and the m here, and the m here, and the m here. But that's interesting because, before relativity, or if you are in frames of reference which don't move, mv is a momentum. Basically the quantity of movement. In relativistic world, and so based on this, we can easily show that the relativistic momentum would be equal to gamma times the non-relativistic momentum, which is mv here. So if we look at this equation here, we can say that the momentum, and we call it p because m was already taken by something else, so I'll call it p like momentum. It's crazy, but so p, the momentum, relativistic here, momentum to the square would be equal to, well, if we look at this, would be equal to gamma mc square minus m square c square, okay, which is what we get here. Right. Now, thank you. So once we have that, we can use what we call in math the Maclaurin series. I don't know if you're familiar with Taylor series, which are more usual. Basically, in Taylor series, you have a here and x minus a here instead of x. And so if you take a equals 0, you get the Maclaurin series. But what's important is that Maclaurin series allows you to give the value of a function, based on its derivative and using some coefficients here. And this is a formula you get, and therefore, if we assume that x is equal to minus v squared over c squared, and we call f of x, the function which yields to 1 over square root of 1 plus x, then this is equal to gamma, 1 over square root of 1 minus v squared over c squared. Therefore, if we apply the Maclaurin series to gamma, which is equal to this, using f of x equal this, then we get something like that. I'll let you do the derivation by yourself. It's pretty easy. Okay? And then, I just said, okay, so this is gamma, but here we have gamma MC. So let's multiply everything by MC and see what happens, okay? So you get gamma MC is equal to MC plus 1 over 2 times mv squared over c. And then some negligible numbers here because there are, CQ and c to the power fifth and even smaller, bigger numbers here mean that these numbers here are negligible. They're so small, you can neglect them. Well, you could if you're not very precise, which was the case before special relativity. And he said, well, that's interesting, because 1/2 of mv squared before special relativity rule was equal to the kinetic energy. So let's see what happened when we multiply everything by c, okay? And so he gets gamma mc squared is equal to mc squared plus, this plus this, blah, 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 which again is, kind of negligible if you consider these numbers are very big, here the c squared and c to the power 4, and etc., etc. And then he said, okay, so well, that's interesting because this is kinetic energy and this is something which doesn't have any movement. There's no speed, there's no distance, time, whatever. It's kind of a constant here. And therefore this is not part of the kinetic energy, and I know that kinetic energy is either exactly that or something very close to that, which would be what I would measure, if I neglect this, because these are too small numbers, So, well, maybe this is the total energy, which means the potential energy of an object or particle plus its kinetic energy here. And so if we assume that this represents the total energy of the object, then we can get from this, p squared is equal to E over c squared, minus the m squared c squared here. Therefore, we get this, from this we get this. E squared is equal to p squared c squared plus m squared c to the 4th power. And this is called, by the way, the energy momentum relation. It's very important. It's used in many derivations in relativity theory. But what's interesting is that when you are not moving, when the speed is 0, and therefore the momentum, which is a quantity of movement, is 0, then you get, so this is 0, then you get ER is equal to mc squared. Yeah, that's right. So since we're not moving, this is the mass at rest, the particle, when it's not moving. Okay. And here you get your, famous Einstein equation, E equals mc squared. Well, and by the way, also you can say that, for massless particles, for instance, photons, photons don't have any mass at rest. And therefore, you get m equals 0, and so the momentum of a photon will be equal to the energy of the speed of light. And by the way, also, there's another thing we can derive from that, which is the fact that here we use the square root, but as you know, the square root can be positive or negative. For instance, the square root of 4 can be 2 or minus 2. And so that means that if you use a negative value, that would yield to the concept of antimatter, which is another matter. Matter. Oh, so funny. Okay, so we won't discuss it here. Okay, but basically, hey, as promised, E equals mc squared. Now, what is the next step? Well, the next step, which seems the most natural evolution is, well, we talked about, Galilean frames of reference, and from, those frames of reference, we could define special relativity. But what would be interesting would be now to use any type of frame reference, including those with acceleration relative to each other, That would be great because, that way we can describe everything. So for that, we just need to do, the same thing as we did for the special relativity, using the Lorentz formulas. We can specify, some transformation mechanism when we want to calculate from one frame of reference to another. And other than that, everything would be similar. It would be actually the same thing, the no privileged frame of reference. But the problem we have with acceleration is that you don't have the same rules applied if you change the frame of reference. Let me take an example. If you remember, the car moving, relative to the ground here, and what we saw with special relativity and Galilean frames of reference is that from inside the car, you could use any physical rule, and the same rules would be applicable on the ground, from a frame of reference on the ground. However, when you get an acceleration in the car, well, the guy inside the car would go, whoa, it was an acceleration and braking, thing like that. So there will be some forces here that would be applied, but the guy on the ground, I don't feel anything. What's going on? Are you drunk or something? So that means, the same rules don't seem to apply for different frames of reference as soon as there is acceleration. So does that mean we cannot apply relativity to non-Galilean frames of reference? Yes, we can, but for that we need general relativity and Mr. Albert Einstein. But that's another story.